About 160,000 light-years away, inside the Large Magellanic Cloud, sits a glowing soap bubble of debris. It is the 400-year-old wreckage of a dead star. But this specific star broke a fundamental rule of astrophysics. It managed to die twice. To understand how a star can die a second time, you have to look at the traditional rules for how they are supposed to explode. Most stars end their lives as white dwarfs, a burned-out core, roughly the size of the Earth, slowly cooling in the dark. But if a white dwarf orbits close enough to a companion star, it begins to siphon off its partner's gas. This diagram shows the mechanism astronomers accepted for decades. As the white dwarf steals material, its mass steadily climbs until it hits a rigid mathematical threshold, exactly 1.4 times the mass of our Sun. At that exact limit, the star can no longer support its own weight. The core collapses, runaway nuclear fusion ignites, and the star blows itself apart. Because this trigger always requires the exact same mass limit, this graph shows how these explosions were expected to release the exact same amount of energy. The fuel is identical, the breaking point is identical, and so the resulting flash should be perfectly uniform. That uniformity was astronomical gold. Because physicists knew exactly how bright these explosions truly were, they trusted them as infallible tools to measure precise distances across the universe. Astronomers call objects with a known identical brightness standard candles. If you see a standard candle that looks dim, you know it is far away. If it looks bright, it is close. These specific supernova explosions are brilliant enough to be seen halfway across the observable universe, making them perfectly reliable cosmic mile markers. This slide shows the 2011 Nobel Prize in Physics, awarded for a discovery that changed everything we knew. By tracking these mile markers, astronomers found the expansion of the universe is speeding up, driven by a force we call dark energy. But as telescopes looked closer at these standard candles, a severe discrepancy emerged in the data. Observers began catching white dwarfs detonating early. They were exploding before they ever gathered enough stolen mass to reach the 1.4 threshold. This created a strict physical contradiction. The entire mathematical model relied on the star becoming heavy enough to crush its own center. If a white dwarf exploded before reaching that threshold, its core could not possibly be the primary trigger for the blast. Every calculation regarding dark energy and the accelerating universe rested on the assumption that we completely understood how these standard candles worked. If the central engine driving our most trusted cosmic yardstick was operating differently than we thought, the baseline measurements for the fate of the universe were suddenly thrown into uncertainty. To solve the math problem, physicists proposed a completely different path for the explosion. They hypothesized that the fatal trigger did not originate deep inside the star's core. It started on the skin. When a white dwarf siphons gas from its companion star, that stolen material is often heavily laced with helium. Over thousands of years, this helium settles across the surface, wrapping the dead star in a highly volatile, dense blanket. Squeeze that helium blanket under the star's gravity, heat it slightly, and it detonates.
The entire outer shell ignites in a violent flash. The surface blast sends a powerful shockwave racing across the star. That wave plunges inward, slamming into the dense core. The extreme compression acts like a detonator, igniting a second, far larger blast. Two distinct explosions, separated by a fraction of a second. This rapid chain reaction allows the star to destroy itself completely from the outside in, entirely bypassing the need to reach the Chandrasekhar mass limit. The double-detonation mechanism worked perfectly inside computer simulations, but it carried an observational flaw. From Earth, the raw flash of those two rapid explosions looked exactly like a standard core collapse. Astronomers could not prove the theory by watching the explosion happen. They had to wait until they could map the specific chemical wreckage an ancient blast left behind in the dark. This is an astrophotograph of SNR 0509-67.5, the 400-year-old supernova remnant. By mapping exactly which elements were present, researchers created a chemical atlas of the debris. A single core detonation creates a relatively smooth, uniform spread of debris. But when researchers mapped the calcium scattered through this remnant, They found a highly distinct structural anomaly. The calcium was forged into two distinct concentric shells, one layer nested neatly inside the other, matching the exact timeline of a double detonation. An outward fling of material from the initial helium flash, followed instantly by the expanding wave of the core blast. This beautifully layered chemistry provides the physical record of two separate shockwaves. The chemical geometry confirms that double detonations happen in nature, moving the theory out of computer simulations and into the physical world. If our standard candles can be ignited by a stolen blanket of helium instead of a crushed core, does the Nobel-winning measurement of dark energy fall apart? This graph shows how multiple explosion paths alter our data. Because some stars explode via double detonation, while others slowly march to the mass limit, they are not perfectly identical clones. They peak and fade with a slightly different true brightness. But this diversity does not break our cosmic ruler. By observing exactly how quickly a specific supernova brightens and dims, astronomers can identify exactly which engine caused the explosion, allowing them to precisely adjust for the small differences in light. Uncovering this hidden complexity actually sharpens our cosmological tools. Knowing precisely how these stars die ensures we can keep measuring the expansion of the universe with extreme confidence. The influence of these exploding stars extends from distant galaxies down to the ground beneath your feet. The extreme heat and pressure generated when a white dwarf tears itself apart acts as a massive galactic foundry. These specific explosions are the primary mechanism for forging the universe's iron. Much of the iron in the core of the Earth and the iron currently carrying oxygen through your blood was cooked in the runaway fusion of exploding white dwarfs. It was scattered across space long before our sun was born. The universe leaves profound, layered records of its history, even in quiet corners. The violent mechanics of deep space are directly responsible for the atoms that make up our world and us.